right, hello, Chem 120 students. This is lecture 2 of 2, maybe 3, depending on how things go today, about thermochemistry. So I wanted to start with just like a brief overview of what the first lecture was. I will be the first to admit that I was a little, I don't want to say rambly, but I definitely wasn't concise in what we talked about. So I'm sorry that it was an hour long. I'll try to make this one shorter, even though it contains a lot more math and a lot more work to be done. Okay, so just a really quick review. We learned about energy and the fact that it is transferred, it's not lost, and it's transferred either in the form of heat or work. And E here would stand for the internal energy of a system. And because we're chemists and we are interested in chemistry, the system is going to be a chemical reaction. Okay, then we also learned about enthalpy, which is abbreviated by H or represented by the letter H. And enthalpy is looking at the total content of energy in a system. And so that's going to be equal to E, the same E as we see over here, plus the product of pressure volume work. And we have this really important consideration that we're going to be applying for all enthalpy problems in this chapter, which is that at a constant pressure, enthalpy is going to be equal to Q. Okay, so then we found one way of determining what Q is, or the heat of a reaction, and that was when we started working with our calorimetry problems, and I think there was a problem with an iron bar being heated up and then allowed to cool. So Q is equal to Sm delta T, where S is the specific heat of a material. And the units are joules per grams degrees Celsius. You can also have the molar heat, which is typically in kilojoules or joules per Kelvin mole. But we are going to really be focusing on joules per grams degrees Celsius in our exploration of specific heat, excuse me. Okay, and specific heat is going to tell us a physical property of the material that we're working with. And it's important to recognize that the higher the specific heat, the more resistant to temperature change. So our example there was water having a specific heat of 4.18 joules per grams degrees Celsius, which is very, very high. So we know that water is very stable, right? Water, our planet's composition of water allows for the temperature on our planet really not to fluctuate that much, especially if you compare it to temperature fluctuations on the planets that immediately surround us, like Mars. Okay, so in contrast, the lower the specific heat of the material would be, the less resistant to change. So if you have a high specific heat, you would be a good insulator, right? Water insulates our planet. If you have a low specific heat, you would be a good conductor, right? And we see that with a lot of the specific heats that we're looking at of metals are really low. Metals are generally good conductors. Okay, so that was our specific heat. So a little review of that. And we found with calorimetry, we were largely using Q equals Sm, Q equals Sm delta T in a way where we're comparing two systems. So ultimately we end up getting Q being equal to negative Q, right? So loss equals gain, or gain equals loss. And that boiled down to a really simple formula that I like. That takes away all of the negatives and allows you to just kind of more directly answer these questions. So where this would be, let's say, our system, and this would be the surroundings. Really, really important equation there. Okay, so we're going to do another example of specific heat that's a little bit more challenging than the one that we did in the first lecture. So here we have aluminum pellets and iron pellets being heated to 100 degrees Celsius and then dropped into some water. It's classic calorimetry. Take something, heat it up, throw it in a pool of water. Okay, so in this case, we're going to be applying that same logic of Q being equal to negative Q. So gain is loss. So here gain is going to be our water. And that would be equal to the loss of our aluminum and our iron loss. Okay, so that's the basic principle that we're going to be applying. So let's isolate all of our variables and just start working away at this problem. This is going to involve a little bit of arithmetic. It's nothing that you shouldn't be comfortable with, but for some of us it might have been a while since we thought about the distributive property or simplifying an equation and whatnot. So let's just go ahead and work through it together. So here we have aluminum. The mass is 5 grams. Specific heat is 0.89 joules per gram degree Celsius. And I see later on in the sentence it says that both the aluminum and the iron are heated to 100 degrees Celsius. So that's going to be the temperature hot of my aluminum, right? Once it drops into water, it's going to cool. All right, so then I can also look at my iron. In my iron, I have a 10-gram sample. The specific heat of iron is 0.45 joules per grams degrees Celsius, and its T hot is going to be equal to 100 degrees Celsius. All right, and the last thing we have is water. So we had a mass, for some reason, of 97.3 grams, and its T cold is 22 degrees Celsius, right? It's going to heat up from there. And remember, specific heat of water will not be given to you in any problem, because you should know it is 4.184 joules per grams degree Celsius. It can't just be simplified to 4.1. Okay, so now we're going to be plugging these variables that we isolated from our problem into our Sm T hot minus T cold. Only now we have two species that are being involved in one side of our equation. So we can think about this as being representative of the water being equal to our aluminum plus our iron, right? Aluminum and iron are losing energy, and the water is gaining it. Okay, now the next thing that we need to recognize is that these species are going to reach a thermal equilibrium. So if you just think about that as like, we have a pool of water, we're heating up these two things of, these two samples of metal, and we're dropping them into water. Eventually, that makes perfect sense. Beautiful drawing, Sam. eventually that water and the metal ingots are going to be at the same temperature. So that is called a thermal equilibrium. So that's really important because we need to be able to recognize that for our water, the temperature hot is going to be the same as the temperature cold for our aluminum and as the temperature cold for our iron, right? That is the temperature of our thermal equilibrium. So we're going to go ahead and replace those values with X so that we are accurately representing the fact that they're the same value. So we have 4.18 joules per gram degree Celsius of water times our 5 grams, oops, sorry, not 5 grams, 97.3 grams. And then we have our temperature hot, which is X for our water, minus 22 degrees Celsius. That is going to be equal to our 0.89 joules per grams degree Celsius of our aluminum times the specific heat of aluminum. Oops, sorry, that's already the specific heat, never mind, times the mass of aluminum times our 100 degrees Celsius minus X. Now that is being added to, sorry, I was worried my dog was going to pee. He's still a puppy. Okay, that's going to be added with the effect of iron. Okay. So we can simplify this problem a little bit by recognizing that on this side of our equal sign, we have a common factor of 100 degrees Celsius minus X. So we can take that out of the two individual parts of this equation and combine it. So our combined equation would look like 4.184 joules per grams degrees Celsius, right? And this is just basic arithmetic. Let me make that a bracket. Okay, so that's our simplified, quote unquote, problem. So I'm going to go ahead and let all of this disappear. So I'll give you guys a second just so you can make sure you have it in your notes. But this last line I'm going to just repeat as soon as I lift up my pen and everything disappears. My one gripe with this program. Okay, so let's go ahead and rewrite it. I'm going to remember that I need a lot of real estate here. And we are going to have, what did I do here? Okay, I'll just rewrite it. We're going to have our sorry, I'm just making sure that I am not doing any of this wrong. Okay, all right, so we would have our 5 grams, which is our aluminum sample, times our 0.89 joules per grams degrees Celsius, plus our 10 grams of iron, times our 0.45, All right, cool. So now we can go ahead and solve for what's in our brackets on one side and we can find the product of 4.18 times 97.3 to kind of get us to the point where we need to start applying the distributive property. So let's see here. This is gonna the sum of these two products of aluminum and iron is going to be 8.95. That's going to be multiplied times 100 minus x would be equal to our 406.7 times x minus 22. Okay, so that's just performing the mathematical operations that we can before applying our distributive property. So that would be 895 minus 8.95x equals 406.7x minus 8,947.4. You should totally check my math. All right, so now I want to isolate our variable to one side of the equal sign. I like to keep numbers positive, so let's just go ahead and add 8.95x to this side. We're doing that to both sides of the equal sign, right? So this cancels out on this side. And likewise, I'm going to bring this value over, and I'm going to add 8,947.4. And now we can simplify those to 9842.4 being equal to 415.65x. Divide both sides by 415.65, 415.65, and you get x being equal to 23.67 degrees Celsius. So we can see from this example that our water really didn't heat up that much, but we would expect that because the specific heat relative to aluminum and iron is very, very high. So that aluminum and iron is definitely going to be approaching the temperature of water, not vice versa. We also have a much larger mass of water than we had of our iron and our aluminum. It's always good after you solve a problem like this to ask yourself if it makes sense. So I just wanted to do that example because I think that's probably the hardest math of this chapter. And like I said, many of you might not have thought about the distributive property for a little while. Okay, so that's calorimetry. And calorimetry is really cool, and it's very specific to a particular combination of things, like we just saw here, the combining of heated aluminum and iron into water. So we know that at constant pressure, which would be that example, right? You have a beaker of water on your desk, you add two hot things to it, that's at constant pressure, right around 1 atmosphere because we're close to sea level. So at a constant pressure, H equals Q, enthalpy equals the heat of reaction at constant pressure. So I wanted to just introduce you to that statement because this is often what you'll end up seeing enthalpy equated to, is heat of reaction. And just know that that's only true at constant pressure, and that's what we're going to be always evaluating. So we already talked about endothermic and exothermic in the last lecture. I think it's just really important to recognize that now, at constant pressure, we have different ways of talking about a system. So endothermic, an endothermic system is going to gain energy. That means the gain of energy of the system means that the surroundings lose energy. So that's what this is saying here. The surroundings get colder in an endothermic reaction. That means that our Q for our system is going to be positive, which means that our enthalpy of the system would be positive. It means that the change in enthalpy of the reaction that we're looking at is going to be positive. In an exothermic reaction, the system is going to lose energy, which means that the surroundings are going to gain energy. Surroundings get warmer. Q is going to be negative. H would be negative, so the enthalpy change of that reaction would be some negative value. Okay, so it's just trying to tie some of those concepts together. And now we're going to see how that applies mathematically and why it is so cool to think about enthalpy. Okay, so here we have silver chloride and it's being dissolved in water. So silver chloride is an ionic compound. You know that. And now we can start to do some really cool analysis. So we have 35 grams of silver chloride. It's being dissolved in, so that's my system, right? Chemical reaction system. It's being dissolved in 100 milliliters of water. Remember that the density of H2O is 1 gram per milliliter, which means 100 milliliters would also be 100 grams of water. And that water is at an initial temperature of 100 degrees Celsius. The solution of water and ions reaches a thermal equilibrium at temperature final 61.7 degrees Celsius. So the question is, how much energy is transferred in the dissociation of silver chloride, right? Okay, so a lot of times when students see a problem like this is basically a calorimetry problem, but it's just not an ingot of something that's being dropped, like some metal that's being dropped into water. Instead, it's a chemical reaction that's taking place. So there's going to be some kind of transfer of heat, and so a change of temperature. And so often students will say, well, I don't know the specific heat of silver chloride, so I can't answer that. And that is not true. We know what's happening in our water, and from that, we can deduce what's happening in our system, right? Because Q equals negative Q. All right, so let's let that go away. And we're going to solve for what the heck's going on with water, and from that, we'll infer what's going on with our silver chloride. So we have 100 grams of water. The specific heat of water is 4.18 joules per grams degree Celsius. And that change in temperature is from a final temperature minus our initial temperature. And that is going to give me what Q is. So plug that into your calculator and you should get a pretty large number. Negative 16009.4 joules. So let's just make that negative 16 kilojoules, right? Love that metric system. Okay, so what's important to recognize here is that this is the effect on our water. So if our water is negative 16 kilojoules, that means that our system would be a positive 16 kilojoules, right? So that dissociation of silver chloride required an input of 16 kilojoules of energy in order to separate those ions. Cool, so energy had to be taken from the water in order to push this dissociation forward, which would mean, right, my delta H would be equal to positive 16 kilojoules, which means that this reaction is endothermic, right? Lost by the water, gain by the system. Okay, so that's a cool statement, but it's very specific to the fact that we had 35 grams of my sulfur chloride. Ugh, that was ugly. If we wanted to make this a more generalized statement, it would be very helpful to, instead of saying 16 kilojoules in 35 grams, it would be great to say how many kilojoules in 1 mole. Very cool. So let's go ahead and do that math. So if we have 16 kilojoules is the amount of energy required gained by the system when we are dissociating 35 grams of aluminum chloride. We can use molar mass in order to convert grams to mole, right? We've been doing that all semester. Let's see, the molar mass of silver chloride is 143.32 grams in 1 mole. Oh, my dog totally has to pee. Okay. That's going to give us 65.5 kilojoules per mole. All right, and that's really useful. Sorry, that's a 6. Because now, if we had, for like any amount that we might have, we would be able to figure out how many, for any mass of silver chloride that we might have, we'd be able to figure out that energy change associated with it. Very cool. All right, so that's that problem, and now we're ready to kind of make this really important transition to talking about enthalpy of reactions. So this change in our delta H would be our enthalpy of this reaction, right? So we just found the enthalpy of the reaction, or which was a dissociation of silver chloride. Same thing could be determined with the combination of iron and oxygen to form iron oxide. So with these mole ratios of 4 to 3, we would generate this much energy, right? This would be an exothermic reaction. So this is the amount of energy that would be released to the surroundings. This reaction here is the same as what happens in those like hot packs that you get for hiking and whatnot. So now we have this question of what happens when 1 mole of iron oxide is produced. Okay, so this value here is specific to the production of 2 moles of iron oxide. So now we need to figure out what would happen if we just had 1 mole. Well, we are going to use our enthalpy of reaction as essentially a conversion factor, understanding that it is specific to this experimentally determined, let me back up. So delta H would be experimentally determined for this reaction. And so we can use our delta H given these proportions of 4 to 3 to 2 in order to answer all kinds of questions, right? We have a conversion factor. We can do all kinds of really cool math. So this is saying what happens if you have 1 mole of iron oxide? Well, we have 1 mole. We know that if we had 4 moles of iron oxide, we would get negative 1,652 kilojoules, right? We have 1/4 as much. So you take that 1,652 kilojoules, divide it by 4, and you should get negative 412.5 kilojoules. All right, so it's just using that relationship given to us by our experiment in order to deduce what would happen if we had less of one reagent. All right, so now we have another problem. Same equation, but we're being asked how much heat is released when 1 gram of iron is reacted. Well, grams don't really tell us that much. So the first thing that you want to do, of course, is get out of grams and get to moles. So it's 55.85 grams of iron is 1 mole. And we know if we had 4 moles, we would get our experimentally determined delta H. You plug that into your calculator, and assuming I did everything right, big assumption, you get negative 7.39 kilojoules. Hopefully you're seeing that this is really useful. All right, now we have another problem. How much heat is released when 10 grams of iron and 2 grams of oxygen are released? Wow, okay, so we're given information about iron, and we're given information about oxygen, and we're asked about the amount of heat produced, right? So the heat produced is a product of this reaction. So you should be thinking, okay, I'm given information about 2 reactants. I'm asked a question about the amount of product. So you should immediately be thinking about your limiting reagent. All right, so let's do it. 10 grams of iron divided by that 55.45, is that right? 85. Is going to give us our moles of iron, which is 0.18. Then we have our 2 grams of oxygen divided by 32 grams per mole. Okay, so now we know the amount of moles that we have, which is important because that's the only way that we're going to be able to get anywhere, right? Because that's putting them on the same scale. 1 molecule to 1 atom in this case. Okay, so now recognize that we have this 4:3 ratio of iron to oxygen. So if we took 4 divided by 3, you would get 1.33. If we took the moles of iron divided by our moles of oxygen, we would get a relationship, what did I get? Of 3. Oh yeah, duh. Okay, so 3 is greater than 1.33, which lets me know that iron is not my limiting reagent. Oxygen is. Okay, that's just a really handy method to try. It's more intuitive for a lot of people if it's just like a 2-to-1 ratio or a 3-to-1 ratio, but this is also really, really helpful. So we know that oxygen is going to be our limiting reagent. We know that if we had 3 moles of oxygen, we would get negative 1,652 kilojoules. So you're going to get negative 34.4 kilojoules. Okay, so the point here is these statements are really, really important, and you can find out a lot of information about all different kinds of proportions of those reactions. I shouldn't say proportions, but all different kinds of masses of those reactions from that. Okay, so this gets us to a really cool relationship that is called Hess's Law, after the gentleman who experimentally proved it. And it states that when reactants are converted to products, the change in enthalpy is the same whether the reaction takes place in one step or a series of steps. Now that shouldn't be groundbreaking, or it shouldn't be a groundbreaking revelation to us, because we've already been talking about the fact that enthalpy is a state function, right? A state function means that all that matters, its current or like that quality. So we've talked about change in enthalpy, change in pressure, change in temperature, change in volume. It doesn't matter what the pathways is, what the pathways are. So the pathway doesn't matter. All that matters is that starting and ending point, right? So it's a state function. So here's a really nice conceptualization of that. So that means that if we're interested in A going to E, that's going to have an associated delta H. Now here we have A going directly to E, but we could just as easily have A going to B, B going to C, C going to D, right? This is that blue pathway, and D going to E. And each one of these would have its own associated enthalpy change. What's really significant is that if you look at this kind of the total number of reactions that we have, in each situation we have a product that then becomes the reactant in the next chemical reaction, right? So these would be considered intermediaries. So these are chemical species that are created in a chemical reaction, but then they're also consumed in that same chemical reaction. So they're not a reactant or a product, but they are a species that is present at a snapshot in time as this chemical reaction is moving towards completion. So we have it as a product here and a reactant there, so we get to essentially cross them out, right? They cancel each other out. They're just intermediates. Same for C, same for D. So the total enthalpy change here would be the same as going directly from A to E. We just took this longer pathway. That would have an associated enthalpy change equal to delta H. If we instead took this pathway, what we would find is that H1, delta H1 plus delta H2 plus delta H3 plus delta H4 would give us delta H. So they would be the same change in enthalpy. One just took a longer way around than the others. So you can think of this as like a direct pathway, whereas this one has intermediates. Okay, so what Hess's law is saying is that it doesn't matter which pathway you take, it's going to be that same enthalpy change. That's going to be really important because as we learned in lecture 2, that enthalpy change is experimentally determined, and we're not always going to be able to do an experiment when we need to know how much energy is gained or lost in a system in the form of heat. So it's really nice if we can use already experimentally determined delta H values in order to figure out what the enthalpy change is for a different reaction. So we can apply Hess's law when we are looking at the conversion of carbon in its graphite form and oxygen gas into carbon dioxide. So let's say we don't know what the enthalpy change is of this, but we do know that the enthalpy change of graphite and oxygen to carbon monoxide is going to be negative 110.5 kilojoules. And we know that carbon monoxide and molecular oxygen combining to form carbon dioxide is negative 283.0 kilojoules, right? And I'm just taking those values off of this chart here. So this would be that second reaction, and this is that first reaction. So we can see that this total reaction can also be identified. So here we have negative 110.5. Here we have negative 283.0. And this is like our target reaction that we're going for, right? So what we want to do is use Hess's law in order to figure out what that enthalpy change is, given that we know the enthalpy change of these two individual reactions. So this is our target reaction. It's important to recognize that when we add our stepwise reactions, so that's what these are called, these are stepwise reactions, and they're used in Hess's law problems in order to determine the enthalpy change of a different reaction. When you look at these, you want to be able to identify that if you have something that is a reactant in one equation or in one reaction and a product in the other, those effectively are going to cancel out, right? So my carbon monoxide, notice, is not involved in my target reaction, the reaction that I'm trying to determine the enthalpy change of. But it is involved in both of my stepwise reactions, but that's okay because it is just an intermediate. It is produced in one reaction and consumed by the other. Another thing to notice is that here we need 1 mole of oxygen. Neither one of my stepwise reactions involves 1 mole of oxygen. They both involve half a mole. But they're both products in both of our stepwise reactions, reactants. They're both reactants in both of our stepwise reaction. We have half a mole and half a mole, giving us 1 mole of oxygen, right? So reactants and products cancel, and if they're on the same side, then the number of moles you have are going to be additive. So this is really cool because then we can say, okay, we had negative 110.5 kilojoules here. We have negative 283 kilojoules here. We can use those two reactions to determine that the enthalpy change of carbon and oxygen going to carbon dioxide would have a total of 293.5 kilojoules just by adding those two numbers. So this is really freeing because it means that we don't have to experimentally determine the enthalpy change at for every single reaction that we're interested in. Okay, so in that example, we didn't have to do any kind of manipulations to the equations in order to get them to cancel out, but sometimes you will have to do that. So let's just talk about what that looks like. So here we have one reaction. So it's water going from its solid form to a liquid form, otherwise known as melting. So here we have the delta H that's associated with that. So that enthalpy change, it's endothermic. We have a gain of 6.01 kilojoules per mole of water. Now let's say here we had a solid melting. Let's say we wanted to go the opposite direction and talk about that liquid freezing. So notice that this equation here is the same as this one, it's just been reversed. And our enthalpy change is equal but opposite. So this is a big concept, which is that the reverse reaction is going to have an enthalpy change of that is also in the opposite direction. So equal and opposite. Same magnitude, but opposite direction. Okay, so I like to call this flipping the equation, right? Reactants become products, products become reactants, and the delta H is negative. Let's say that in our reaction, we needed to have 2 moles of water, solid water going to liquid water. So if I need 2 moles and I have this as my delta H, then I would need to multiply this entire system by 2, right? I have to do it to the whole thing because this thermochemical equation, or this enthalpy change for this reaction is specific to the conditions of 1 mole to 1 mole. but as long as they do it to everything, all is fair. My delta H now would be equal to 12.0 kilojoules. So if you reverse the direction, the sign of delta H is reversed. If you need to multiply the number of moles or divide them, you need to do the same thing to that enthalpy change. Right? Very similar concept to what we did in the second lecture where we were looking at that iron oxide reaction. Okay, so one really important thing to remember is that states are going to matter. There's two T's there. So solid going to liquid, that enthalpy change is 6.01 kilojoules. So that solid ice needs to absorb 6.01 kilojoules per mole of water that you had. What does that mean? If you had 18 milliliters of water, you would need to supply it with 6.01 kilojoules in order to melt all of that ice to liquid. Here, if we have a liquid going to gas, we would need 44 kilojoules, right? So if I had that same amount, I have 18 grams of water, which is representing 6.022 times 10 to the 23rd molecules of water, 1 mole. I would need to give it 6.01 kilojoules to go from solid to liquid. If I wanted to then go to gas, I would need an additional 44 kilojoules per mole. Right? So water will melt much more readily than it will go into a gaseous form. That has to do with its intermolecular attractions, which you'll learn about in Chem 2 when you take it, because you love chemistry so much. Okay, so let's do an example where we need to do some of those manipulations in delta H so you can see what that looks like. So calculate the standard enthalpy of formation of CS2, carbon disulfide, given that these reactions that we have here. So these are our stepwise reactions. So we are going to use these steps in order to get a final / target reaction. And ultimately the question is, what's the delta H of this reaction? Okay, so I always like to tell students to work backwards here. So what I do is I look at, okay, these are my my reactants of my target. Right, so these are the species that I need to make sure once I add or do all of my manipulations to my stepwise reactions, those are going to be on the reactant side and they're going to be in those proportions. So first I identify my reactants in my target equation, and then I find those in my stepwise. So I have carbon in its graphite form in my first stepwise reaction. I have sulfur in its rhombic form, that's one of its solid forms. And then, oops, I guess that changes everybody's color. Okay, well I won't bother with colors then. Let's go back to red. Okay, so underlining these, right? Now I like to box my products. You don't have to do this, it's just my way of making sure that things are on the right side. So here I have my product in my stepwise reaction. Make sure that you're not missing anything. Sometimes you can have products in multiple places or reactants in multiple places, but it looks like we are good. So then the next thing I like to do is if I have to flip any of my reactants, I go ahead, or my stepwise reactions, I want to go ahead and do that. So the first thing I do is identify. The next thing I do is flip. Then I will multiply or divide, and then I kind of solve it. So identify reactants and products, flip anything that needs to be flipped. So in this example, my carbon disulfide is a reactant in my stepwise equation, but I need it to be a product in my final equation. That means that I have to flip that entire reaction. So that is going to give me CO2 plus my 2 S2O going to 3 O2 plus my CS2. So now I have my CS2 on the right side of the equal sign, which is great, and I need to remember that my delta H of that reaction is now going to be positive. So I like to keep kind of a tally of what I've done to my delta H's on the side here. Okay, so I know that that's how I'm using that equation. Next, I have my carbon graphite as a reactant. That's what I want. My rhombic sulfur is also a reactant. But notice I need 2 moles of my sulfur in order to get the reaction that I am looking for. So that means that I'm going to multiply everything here by 2. All right, so that gives me my 2S plus my O2 going, 2O2 going to 2SO2. So because I multiplied my equation, I need to make sure that that is done to my delta H of my reaction value too. So that's negative 296.1 times 2 is going to be negative 592.2. All right, and there's no manipulation that I needed to do with my first equation, so I can just leave that as it is. Okay, so now I want to make sure that everything cancels out. So I'm going to actually let this clear so that we can see what that looks like. All right, so these are the manipulations that I made. This needed to be flipped. So now it's CO2 plus 2SO2 going to CS2 plus 3O2. And these all have a 2 in front of them. Now this is positive, and this is negative 592.2. Okay, so now I want to make sure that the things that I need cancel out, and we are going to identify those intermediates. We're going to figure out, okay, we have the total number of moles that we need. So looking at this, I can see, okay, I have carbon dioxide here in a couple different places, and I don't need that in my target. So does it cancel out? And sure enough, it does. Here, it's a reactant. Yeah, let's get it out of there for reals. And here, there it's a product, and here it's a reactant. Okay, I also have 2SO2 here that I don't want in my target. Does that get canceled out? And sure enough, it does. Right, I've already effectively canceled this guy out just by flipping it above. Okay, so forget that. Okay, so now I have my carbon, I have my oxygen, I have my 2 rhombic, I have my SO2, so the only thing I need to get rid of now is my oxygen. So I have 3 oxygen as a product, and I have 2 oxygen in one of my stepwise reactions and 1 in the other as reactants. So 2 plus 1 would be 3 moles total of oxygen in my reactant side of my stepwise reactions, and I have 3 moles on my product side over here, so those cancel out. So now check your work and drop things down. So we have C plus 2S is CS2. Awesome. So now I want to figure out what my delta H is. Right, so just verified that these match. Yay. Now I need to add up. I needed all of those stepwise reactions, so I'm going to add negative 393.5 plus negative 592.2 plus 1072. And you get a total enthalpy change of 86.3 kilojoules per mole would be the delta H of this reaction. So it's pretty rad. There's some great Hess Law problems in your recitation. I also included a link to a website that has some nice additional ones. All right, so that's Hess Law. This is a really cool challenge problem. If you want to do it, maybe I'll give you some extra credit points. Cool. Yeah, let's do that. So let's say if you solve this, I'll give you plus 5 points on your lowest exam. Yeah, that's big. That's a bribe. That's a bribe to do it. Do it. Okay, this is really fun. So you can send it to me by email. Submit via email. All right, and you have to show your work. So take a picture of your work. Yeah. Okay. I'm not going to do it here because that would defeat the purpose of bribing you, wouldn't it? Okay, so that's one way that we can determine the enthalpy change of a reaction without having to do the individual experiment ourselves. Another way is by using our delta H of formation. So delta H of formation is talking about the enthalpy change involved in the formation of that chemical species at a standard state. So this, we say not to represent that. It can also be prime. And those are under our standard conditions. Standard conditions are going to be different for enthalpy versus entropy versus Gibbs free energy. So it's specific to what exactly it is that you're studying. In this case, we're looking at enthalpy, and that is going to be at 1 atmosphere and 25 degrees Celsius. All right, this is essentially room temp and pressure for those of us who live near sea level. Okay, so standard state, if you think about the standard state of something, it's going to be in the phase that you normally associate it with. So for instance, the standard state for oxygen would be a gas. Standard state for sodium would be a solid. Standard state for mercury is a liquid, right? Think about every sample of liquid that you've seen every sample of mercury that you've seen in thermometers, in Terminator 2. It's a liquid form. Sodium, solid. Oxygen would be gas, right? So these would be their standard states. And so we're going to use the enthalpy of formation in order to figure out what an enthalpy change is of a chemical reaction. And what that requires is examining what the enthalpy of formation is for each of the individual species that are engaged in that reaction. So what's important is that all species in their standard state have an enthalpy of formation of 0, which makes sense. There's no energy required or released by oxygen when it is at 1 atmosphere and 25 degrees Celsius. That is its like native state. It would be in its gaseous form. If you were to, take sodium and make it a liquid, you would have to provide it at 1 atmosphere and 25 degrees Celsius with energy in order to melt it. So it is not at its standard state if it was sodium, liquid sodium, whatever. Okay, so let's see what this looks like in action. And again, the point here is that you don't have to do an experiment for every single thing that you are interested in. So we have this great equation that students always kind of want to puke at. Oh, hey, do you guys want to see my dog? Hey, Dora, come here. Oh, you love me. Okay, this is Dora. He's very cute. He's a puppy, so he really likes to bite. You had to pee earlier. That's why you have 3 videos instead of 2. Yeah, I love him. He loves me. He's adorable, right? Little German Shepherd. He's 4 months old, almost 5. Aren't you? Ooh, loves being picked up. Okay, sorry. Little cameo by the dog. So this we just like to call, loves attention, the summation equation. And so what this is saying is that we can use those delta H's of formation, and if we find their total value for the products and we subtract that from their total value for the reactants, we can find the delta H of that reaction in a standard state, 1 atmosphere and 25 degrees Celsius. Okay, so this is our equation, and this means the number of moles that you have. Delta H is going to be specific to each of the species that are involved in our reaction. So here's an example there, right? Lowercase a would be the number of moles, A would be the species. So to plug this into our equation, this is a reactant, so it's going to go on this side of our equation. Lowercase a would be our number of moles of A. Delta H of formation would be specific to A. Hold on 1 second, sorry. Go ahead. Working from home. Would be our delta H of formation, and A is going to be whatever that species is. Right, so we're going to take that delta H of formation and multiply it by the number of moles that we have, is basically what that breaks down to. So this is kind of our summation equation. We call it summation because this stands for sum of. Okay, so let's do an example, because I know for a lot of people you're probably like, what the heck are you talking about? Okay, so we have benzene burns in air to produce carbon dioxide and liquid water. How much heat is released per mole of benzene combusted? The standard enthalpy of formation of benzene is 49.04 kilojoules per mole. Okay, so here we have benzene, we have oxygen combining carbon dioxide and water, classic combustion. So we want to figure out what our delta H of this reaction is. And so this is our equation that we're going to be applying. And this would be the delta H's of formation that you would be given for each of the species. Now, if you are not given the delta H of formation of something, you can assume safely that it is already in its standard state, and thus the delta H of formation of that species at 1 atmosphere and 25 degrees Celsius would be 0. It's already existing in that state. Okay, so our delta H of reaction is equal to the sum of our products times the number of their moles minus okay, so it's kind of a simplified version of that same equation. So let's go ahead and apply it. So our delta H of formation would be equal to, we want to look at our products first, right? So we have carbon dioxide, we have 12 moles of CO2, and that enthalpy of formation is negative 393.5. I'm going to add that to the enthalpy of formation of our water, putting brackets around that because that's done first. So the product of that is going to have our next step subtracted from it. And that is looking at benzene. So I have 2 moles of C2H6. I guess for whatever reason I wanted to write the unit on that one, but none of the others. And notice oxygen has no enthalpy, oxygen has no enthalpy change associated with it, so I don't need to add anything to that, right? Because its enthalpy change of formation would be 0. Okay, so we can just go ahead and solve that, and we should get negative 5946 kilojoules. So for this reaction, using our delta H information, we know that we get negative 5946 kilojoules. Now that's for this specific reaction, and we are asked how much heat is released per mole of benzene. So now we have this one additional step, because remember that this value is specific to the ratios that are given in our balanced chemical equation. So that would be in 2 moles of our C6H6, right? And we want it to be 1 mole, so we'll just divide that number by 2. And you get negative 2973. Right, and that could be useful and used for all different kinds of things, as we've seen in previous slides. Again, lots of examples in your recitation packet. You're going to want to practice that. This is just a table of some common enthalpies of formation that I wanted to include because there's a couple questions in the recitation packet where it doesn't give you the delta H formation, or it might be owls that you're not given it, and this is just a really handy resource.